What if the oldest galaxy ever seen is proof our universe exists inside a black hole? Astronomers have just spotted something that shatters everything we thought we knew about the cosmos. Thanks to the James Webb Space Telescope, scientists have discovered a tiny, brilliant galaxy called MAMZ 14, blazing into existence less than 300 million years after the Big Bang. This faint, distant speck of light is forcing experts to rethink the entire timeline of how stars, galaxies, and even matter itself came to be. If MAMZ 14 is real, and all the evidence currently supports its existence, then our oldest cosmic models are missing something massive, a fundamental piece of the puzzle that's eluded generations of astronomers. But the mystery goes deeper still. Some leading physicists now argue that MAMZ 14 hints that our universe is far stranger than we ever imagined. What if every galaxy, every star, every atom, everything we know is trapped inside a black hole? It sounds impossible, almost science fiction, but this radical idea is gaining momentum in scientific circles, fueled by discoveries like this. Let that sink in for a moment. Picture the universe at that time, not yet 1 billion years old, still echoing with the aftershocks of its own birth. Matter only just beginning to coalesce out of blinding plasma. According to every established model, galaxy formation should have taken hundreds of millions, if not billions of years longer. Yet here is MAMZ 14 already teeming with stars and complex, heavy elements, when the universe should have barely settled from primordial chaos. Refusing to face these discoveries means clinging to an outdated, incomplete vision of reality, and missing our chance to understand the universe's true nature, its origins, and perhaps even our own place within it. So what exactly did the James Webb Telescope find? And why does MAMZ 14 break all the rules? To answer that, we need to dive into the mystery of ancient galaxies and the extraordinary tools we now use to uncover them. What transformed the James Webb Space Telescope from a simple telescope into humanity's most daring time machine? In the year 2022, after decades of planning, the James Webb Space Telescope, known as JWST, left Earth's surface, journeying to a lonely point nearly 1.5 million kilometers away. This remote post, far beyond the moon, sits at the second Lagrange point, a perfect balance of gravity and shadow, where JWST can watch the universe in uninterrupted darkness. The journey itself was an engineering feat, comparable to the Apollo moon landings in ambition. JWST's gold-coated mirror, measuring over 6.5 meters across, had to be folded and carefully unfolded in space, like a high-stakes piece of cosmic origami. The sun shield, the size of a tennis court, unfurled to protect its delicate instruments from the heat and light of the sun, ensuring that its sensors could remain cold enough to detect the faintest traces of ancient light. Unlike the Hubble Space Telescope, which revolutionized our view of the cosmos with visible and ultraviolet images, JWST was designed for a different mission. It sees in infrared light, the ancient, stretched-out glow that has traveled across nearly 14 billion years of cosmic expansion. By capturing these faint signals, JWST peers further back in time than any instrument before it, opening a window onto the universe's earliest chapters. Hubble once stunned astronomers by revealing galaxies more than 13 billion light-years away, like GNZ 11, a galaxy whose light began its journey when the universe was just a few 100 million years old. Yet even Hubble, with its smaller mirror and aging instruments, could only go so far. There was a cosmic frontier it simply could not cross. JWST broke that barrier. Its gold-plated mirror, more than twice Hubble's diameter, and its exquisitely sensitive detectors opened a new window to the earliest chapters of the universe. If the universe's entire history were compressed into a single year, Hubble let us peer back into December, perhaps to the 29th or 30th. JWST, however, lets us glimpse New Year's Day itself, witnessing the very first fireworks of cosmic creation. But what exactly did JWST see out there in the primordial dark? And why do its discoveries challenge the very foundations of modern cosmology? Their discovery forced scientists to question everything. How could galaxies grow up so fast? How could stars and metals appear so soon, when the universe was still in its cosmic infancy? These findings threaten to overturn the established story of how matter, stars, and galaxies first emerged. If we underestimate what JWST has revealed, we risk missing the magnitude of this revolution, a scientific upheaval that could rewrite our understanding of the universe's origins, timeline, and the laws that shape reality itself. The results were breathtaking and deeply unsettling. JWST detected galaxies that, by every accepted theory, should not exist. These galaxies, like the enigmatic MAMZ 14, were not just old and dim. They were astonishingly bright, compact, and chemically evolved, appearing mere hundreds of millions of years after the Big Bang. They glittered with heavy elements and new stars, features that should have taken billions of years to develop. How can a galaxy be so mature when the universe itself was barely out of cosmic infancy? To understand the true impact of JWST's revelations, we must follow its gaze into the earliest ages of the cosmos. What it found there could change everything we thought we knew about how the universe began. Let us examine JADE's GSC 13-0. This galaxy existed only 320 million years after the Big Bang, a time when the universe had not even reached 1 billion years old. Its age was pinned down by a redshift of Z equals 13.2, meaning its light has journeyed for more than 13.5 billion years to reach us. Soon after, astronomers spotted something even more astonishing. The galaxy MAMZ 14 emerged in the new data, and it is even older, just 280 million years after the Big Bang. Its redshift is a staggering 14.44, making it the most distant and earliest known galaxy ever observed. Both JADE's GSZ 13-0 and MAMZ 14 are compact, dazzling, and brimming with newborn stars. But what truly stunned scientists was their chemistry. These young galaxies show unexpectedly high levels of nitrogen, a chemical element that can only build up over several generations of stars living and dying.
This discovery shattered expectations. According to the standard cosmological model, galaxies should take hundreds of millions of years to forge heavy elements after the Big Bang. Instead, these galaxies seem to have raced through multiple cycles of star birth and death in what amounts to a cosmic eye blank. Their rapid star formation and advanced chemistry defy the rules we thought governed the universe's early days.
If galaxies could form and mature at this pace, then our entire cosmic timeline might be wrong. Years of scientific consensus about the universe's beginnings are suddenly at stake, forcing astronomers to question the very bedrock of cosmology itself. To put this into perspective, consider the Milky Way galaxy. Our own galaxy is over 13 billion years old and has taken billions of years to build up its heavy elements through generations of stars. Yet MAMZ 14, less than a tenth as old, already shows signs of advanced chemical evolution. It is as if you met a toddler who could recite Shakespeare and solve calculus problems. Clearly, something is off with our expectations. And the surprises do not stop there. The James Webb Space Telescope is revealing even stranger sights that threaten to upend our deepest assumptions. What if these galaxies are not flukes, but clues to a deeper cosmic secret? Stranger still, MAMZ 14 shows no trace of a supermassive black hole at its center. That breaks a cardinal rule. Nearly all galaxies with intense star formation should be anchored by these titanic dark engines. In the local universe, galaxies like the Milky Way or Andromeda all have supermassive black holes millions or even billions of times the mass of our Sun. Their gravity helps shape galactic structure and regulate star formation. The absence of such a black hole in MAMZ 14 defies this pattern and asks us to look for new explanations. These discoveries echo past scientific revolutions. In the early 20th century, Edwin Hubble's discovery that the universe was expanding shattered the static universe model. In the mid-20th century, the detection of cosmic microwave background radiation confirmed the Big Bang. Now, JWST's findings may be the next upheaval, challenging our models at the most fundamental level. The James Webb Space Telescope has not found just one oddball. It has uncovered dozens. Astronomers call them little red dots, tiny ancient galaxies ablaze with new stars, appearing only several 100 million years after the Big Bang. These are not rare exceptions. The young universe was crowded with these rapid-fire star factories. For example, the CERS survey by JWST has cataloged more than a dozen galaxies with redshifts above 13, each one a candidate for the title of earliest known galaxy. The sheer number of these objects suggests that rapid galaxy formation was not a rare event, but a common feature of the early universe. In some survey fields, astronomers have found more of these galaxies than predicted by leading models by factors of 10 or even 100. But this is where the trouble starts. The leading models, like lambda cold dark matter, or LCDM, cannot explain how such galaxies formed so swiftly or became so chemically advanced in so little time. Their existence breaks rules that scientists have trusted for decades. Do we need to rewrite the laws, or have we missed something hidden in plain sight? Some physicists are considering an extraordinary idea. What if our universe was born inside a black hole? This bold theory, known as black hole cosmology, rewrites the origin story. Instead of a single Big Bang, there could have been a bounce, a universe emerging from a black hole in a parent cosmos. In this cycle, each universe is born from the collapse of stars and the formation of new black holes, repeating endlessly. The implications deepen with the Einstein-Cartan theory, which tweaks Einstein's general relativity. Here, space-time is not just curved, but twisted. This extra twist, torsion, could stop a true singularity from forming inside black holes. Instead, it may ignite a new burst of expansion, a big bounce, giving rise to a fresh universe beyond the event horizon. So, is the universe hiding its true nature in the data, or are we only seeing what we expect to find? Before we leap into new universes, we must confront the hard limits and possible blind spots of our own observations. Consider historical parallels. When Copernicus proposed that the Earth orbited the Sun, not the other way around, he was met with skepticism and resistance. Yet that idea ultimately revolutionized science and our understanding of our place in the cosmos. The black hole universe theory, if validated, could be our generation's Copernican moment. If this is true, the radical galaxies uncovered by James Webb are not mistakes. They are signposts, hinting that the universe is far stranger and perhaps far more cyclical than anyone dared imagine. Accepting a black hole universe would mean discarding cherished models, risking scientific credibility, and shaking the very core of cosmology. Are we deciphering the true whispers of the cosmos, or misreading echoes, letting wishful thinking masquerade as revolution? But what if the answers are buried in the way we gather and interpret the evidence? The debate now turns to the limits and potential illusions of our cosmic measurements. A constant threat shadows every measurement, the risk of overestimating a galaxy's distance or age. A subtle misinterpretation of a spectral fingerprint, or mistaking a nearby object for a primordial one, could send us chasing ghosts. At the far edge of the observable universe, every calculation teeters on a knife edge of uncertainty. Before we rush to rewrite the universe's history, we must anchor ourselves in the discipline of scientific skepticism. Gauging redshift at these distances is a daunting feat. The farther we look, the more attenuated and stretched the ancient light becomes, increasing the odds of mistakes. That's why only spectroscopic confirmation can separate a genuine breakthrough from a mirage. Even assuming the data hold, the story is far from clear. Galactic rotation, gravitational lensing, and the hidden hand of dark matter all twist the narrative. Invisible halos of dark matter may be turbocharging the growth of ancient galaxies, helping them shine where our models expect darkness. Maybe the universe is not breaking its rules. Maybe we never truly grasped those rules at all. To illustrate, consider the case of galaxy GNZ 11. Originally, Hubble data suggested it was the earliest known galaxy, but subsequent analysis with JWST revealed even older objects. This shows how rapidly our understanding can change as new instruments come online. In some cases, what appeared to be ancient galaxies turned out to be foreground objects masquerading as distant ones due to overlapping colors and confusing signals. It is a reminder that in astronomy, as in life, things are not always as they first appear. The questions only deepen as we weigh what Webb's discoveries truly mean. If these galaxies are real, the foundations of cosmic history tremble. Is it possible that the universe experienced a period of hyper-accelerated growth, a cosmic inflation far more complex than we imagined? Or are we glimpsing evidence of new physics, forces or particles yet undiscovered that shaped the universe in its youth? This is the razor-thin line that science must walk, the tension between chasing discovery and guarding against self-deception. One false positive, a single galaxy wrongly identified, can cost years of inquiry and millions in resources. Yet if we cling too tightly to doubt, we risk missing the rare paradigm shifts that redefine everything. Each new cosmic clue must be scrutinized, challenged, and re-verified, because what hangs in the balance is far more than academic pride. These findings threaten to upend humanity's very sense of its place and purpose in the universe. Some scientists are exploring the possibility that the early universe was denser and cooler than previously thought, allowing galaxies to form more quickly. Others speculate about exotic forms of dark matter, or even entirely new dimensions of spacetime. Each hypothesis opens new avenues of inquiry and new risks of being wrong. To move forward, astronomers are developing new techniques and instruments. For example, large ground-based telescopes like the Extremely Large Telescope in Chile and the 30-meter telescope in Hawaii will soon join the hunt, offering higher resolution and deeper sensitivity. By combining their data with JWST, we can cross-verify discoveries and reduce the risk of error. International collaborations, such as the Vera Rubin Observatory's Legacy Survey of Space and Time, are poised to provide even more comprehensive maps of the cosmos, helping us trace the evolution of galaxies across billions of years. The universe is stranger than we dared to dream, and discovery is only beginning. We find ourselves at the edge of an intellectual chasm, gazing into a cosmic unknown more baffling than our boldest theories could predict. If these revelations are true, everything we believed, the timeline of the universe, the birth of stars and galaxies, even the fabric of space and time, may need to be rewritten from the ground up. Each new image, each faint and impossibly distant galaxy unveiled by the James Webb Space Telescope reminds us that the cosmos is not a finished story. It is a living, breathing mystery. Galaxies like MAMZ 14, already ancient and chemically rich, though born just a few 100 million years after the Big Bang, should not exist. Yet, the evidence is written across the night. This is not just about distant galaxies or abstract physics. Our deepest understanding of reality, our place among the stars, and the meaning of human existence are at stake. Do we cling to old models, or do we dare to embrace wonder, skepticism, and the radical possibility that our universe may dwell within the heart of a black hole? The cosmos calls for explorers bold enough to wonder. Will you answer the call? The implications reach beyond astronomy. The possibility that our universe exists inside a black hole raises profound philosophical questions. What does it mean for causality, for the nature of time, for our sense of free will? If universes can spawn from black holes, could we, someday, create universes of our own in the laboratory? Theoretical physicists have begun to explore these possibilities, sketching out scenarios in which advanced civilizations might influence the birth of new universes, a cosmic legacy beyond imagination. We risk missing the chance to reshape not only astronomy, but our very sense of who we are. Or, by staying curious, we might discover a truer sense of belonging and origin. The greatest breakthroughs begin with questions that seem impossible. So as you look into the depths of space, remember, the universe's story is still being written. The more we learn, the less certain we become, and that is a gift. It invites us to keep questioning, keep exploring, and never take reality for granted.